This conference will now be recorded.
Good morning, one and all. This is Rajesh. In our subject Embedded System Design, we will cover our Unit 4 RTOS based Embedded System Design in this video. So, the topics in this chapter are RTOS based Embedded System Design, consisting of objectives, introduction, operating system basics, types of operating systems, tasks, process, threads, multiprocessing, multi-threading, and task scheduling. So the textbook is Introduction to Embedded System by Shibu KV. What is our objective is, you should just define what is an embedded system, because your operating system topic is related to embedded system. So then understand the operating system concepts and relate them to your embedded systems. Know the topics as task, process, and threads, and how they are related to OS, and how multiprocessing, multitasking, and task scheduling is done in an RTOS. So coming to introduction, as we have seen in our day-to-day life, we are using a number of products which are digitized and they are built around embedded systems. So we can say that embedded system is a unique system and the hardware and the software is specialized. And what is the purpose of designing embedded system? In order to meet a special task. So what are the applications? Household applications, telecommunications, medical equipment, industrial control, consumer products, etc. So coming to definition of embedded system is an electromechanical system designed to perform a specific function. So it is an electromechanical system designed to perform a specific function. It is a combination of hardware and software. In our terminology, it is called firmware. The other name for a software is a firmware, and we are dealing with embedded firmware. Embedded firmware is nothing but a application software program or the control algorithm. It tells how your embedded system must behave for executing a task, how a hardware along with the peripherals must behave in order to execute a task. And these embedded system will run by its own without human intervention, and they are required to respond to events in real time. So these are some examples of embedded system as we covered in our previous videos. So these microwave ovens, washing machine, digital camera, smartphone, air navigation system, flight control system, traffic light controllers, metro rail. So they all come under embedded systems because there is a hardware and some application software, the control algorithm, the program code which is stored in the memory is going to tell how a embedded system will behave. And these embedded systems are classified into small scale, medium scale, and large scale. Small scale systems are such as your electronic toys, where the application program will tell how a toy should operate. But whereas medium scale and large scale embedded systems require one operating system which provides a mechanism, or it is supervising the application software. We can tell as operating system is a real time, because now embedded systems are the other definition for embedded system is microprocessor or microcontroller based system doing a specific task and responding to events in real time. So it has to respond to events in real time. So that's why your embedded system is called a reactive system. So in order to respond to events occurring in real time external world, it requires a sensors. In order to generate the output, it requires actuators. And this control mechanism is done by your RTOS. This RTOS stands for real-time operating system, which supervises the application software and provides a mechanism to let the processor run a process as per the scheduling. by following a plan to control the latencies. See, RTOS is defining the way the system will work. It sets the rules during the execution of application program. So once again, I'm saying RTOS is nothing but the core of the hardware and the application software in the memory. They are together performing a specific task. So when it is performing a specific task, there may be a number of subtasks, and all subtasks will be monitored. They are scheduled and prioritized, and how our embedded system will behave. So that is related to processor specific. How the processor is going to execute. So this execution is controlled by operating system called real-time OS, which is defining the way the system is going to work. So all small scale systems will not require RTOS. Only the medium and large scale embedded systems will require this RTOS. So what is an operating system? Operating system is also a software part which is stored in a permanent memory called ROM, and it is acting as a bridge between the user or the user applications or the tasks and the underlying resources. Means this OS is going to decide based upon the occurrence of the tasks and which resources must be allocated for that purpose. So thus OS is acting as an interface between user and hardware. So if you see this schematic, there the below diagram tells there is a hardware like printer, mouse, monitors, or some other devices which are separated by an operating system to the user interface program. What is the user interface program? A web browser, a email reader, and a music player. These all come under user code, and these are separated by an hardware. So user applications are met by your OS, and OS has a core element called kernel. Kernel has a set of services. What service a kernel can do is it does memory management. So dynamic allocation, deallocation is done. Whenever some task is completed, memory must be emptied. Whenever a task requires intermediate data, it must be stored in RAM. So this memory management, process management. Here the task or the process is can be used for either way. So all the tasks or process must be managed. Which one should go, which one should happen, which task must be executed, which must be held, which must be interrupted. So all that is done by your kernel. Time management. So it cannot allocate CPU time, processor time for only one task. It has to take care of all the tasks. So they can go for pipelining method or any other technique so that your time is managed and your memory is managed, your process is managed. Then file system management, where the files are stored and which file must be executed. Then input output subsystem management. Input output subsystems means your LEDs, buzzers, optocouplers. These are the all the input output systems. So their system management is also done by the kernel. So kernel is the core element of your operating system. This kernel operating system is connected to your user applications through an interface called application programming interface, and these kernel services are connected to your underlying hardware through device drivers. What is a device driver? Whenever you connect an USB, this USB will tell what is the data transmission rate, whether it is serial or parallel. So that is all stored in the device driver. So once if you connect any external device to your embedded system, it will identify by studying the device drivers. Then only data exchange takes place through kernel services from the user application to the underlying hardware. So your kernel is the core of the operating system. It is responsible for managing the system resources as well as communicating among the hardware and other system services. A kernel acts as the abstraction layer between system resources and the user applications. So as we told, it is acting as a interface between system resources and user applications. It contains a set of libraries and services. It contains a set of system libraries and services. So there is a general purpose operating system, there is a real-time operating system. General purpose operating systems are like Windows, Unix, Linux, which are stored in our desktop computers. So Windows, Unix, and Linux are stored in the desktop computer, whereas real-time OS such as VxWorks is used for embedded system. So embedded system can use both general purpose OS some requirement like industrial automation. You may not require real-time OS. For industrial automation, a general purpose OS is sufficient. So there, in medium scale embedded systems, you can use an general purpose OS. Whereas if you go for RTOS, that is used for large scale embedded systems. So large scale embedded systems will use this RTOS. So we'll see what is the general purpose OS. The kernel contains different services like process management, primary memory management, file system management, input output system device management, secondary storage management, protection, time management, and its is interrupt handling. So these services are done by a kernel. Kernel is a small program code of the OS which is stored in the memory. So and whenever some algorithm is executed, so whatever the intermediate data is generated, that is stored in a user space. So the program code corresponding to the kernel applications are kept in a continuous memory of primary and is protected from unauthorized access. So this operating system must not be disturbed by any other user other than the vendor itself. That's why this kernel space is allocated for your OS, where kernel and its set of services of OS will be stored, and the user space is allocated some primary memory. Uh, the partitioning of memory into kernel and user space is purely depending on the OS, and an operating system with virtual memory support will load user applications into corresponding virtual memory with the demand paging technique. So if you don't have sufficient memory, you can utilize this demand paging technique, where a virtual memory support is utilized to load the user applications with corresponding virtual memory space. And most of the operating systems will keep the kernel application code in the main memory, and it is not swapped into the secondary memory. Secondary memory is an memory, it is connected externally through an USB. So kernel space is related to operating system kernel and its services, whereas user space is related to intermediate data generated during the execution of application software. So monolithic kernel, all kernel services will run in a kernel space. So there are two types of kernels. One is monolithic and microlithic. If you go for monolithic kernel, you have to see that all the services are kept in a kernel space, and these modules will run within the same memory space under a single thread. So all kernel modules run within the same memory space and a single kernel thread. The tight interaction of kernel modules in monolithic follows the effective utilization of low-level features of the underlying system. So the tight internal integration of kernel modules in monolithic kernels architecture allows the effective utilization of the low-level features of the underlying system. The major drawback of this system is if any failure is occurring, it will crash entire kernel services. Example of Linux, Solaris, MS-DOS, they come under monolithic kernels. So where this monolithic kernel is this monolithic kernel with all operating system services running in kernel space. So this you can see application software connected through an OS to a monolithic kernel. So microlithic kernel, it incorporates only the essential part of your OS in the kernel space, and remaining part it is stored in a separate memory space called servers, and these servers uh, are run in user space. See, the rest of the operating systems are implemented in program known as servers, which run in user space. The kernel design is highly modular, provides OS neutral abstraction. Kernel services running in user space are called servers. So if you see the uh, application management, timer systems, interrupt handlers are examples of essential services which form the part of the kernel. So all essential services will be kept in kernel space, non-essential services will be kept in user space, and those services of kernel which are kept in user space are called servers. And what is the advantage of benefit of this microkernel is robustness and configurability. What is robustness is if a problem is encountered in any services, it is reconfigured and restarted without the need for restarting the entire OS. Configurability, any services which run as server application can be changed without the need to restart the whole system. So some of the services they get interrupted, so those services can be restarted without going for restarting the OS. So this is the diagram where microlithic kernel with essential services is kept in kernel space, and in the application all the applications running on the embedded system are connected to your kernel space and user space, and in the user space we are keeping a servers. These servers will contain non-essential things of your kernel. So types of operating system. Operating system is a set of services providing an interaction between user space and the hardware resources. So depending on the type of kernel and kernel services and what is the purpose and type of computing systems, where OS and is deployed and the responsiveness to the applications, your operating system is classified into two types. One is general purpose OS, another is real-time purpose OS. Under general purpose OS, we have where the kernel is generalized and all the services execute general applications, and they need not be deterministic. So your this OS will not see that your output is deterministic and may inject some random delays into the application software, and thus cause slow responsiveness of an application at unexpected times. So where deterministic behavior is not important in such a places, we go for general purpose OS. And example is our personal computer system where Windows XP, MS-DOS, these are our general purpose operating systems. And operating systems which are deployed in embedded systems demanding real-time response, deterministic behavior, implementing scheduling policies, and implementing policies which are time critical allocation. So example, Windows CE, QNX, and VxWorks. Windows CE, QNX, and Windows CE, QNX, and VxWorks, micro C / OS2. These are examples of real-time operating system. So normal general purpose operating system is Windows, Linux, MS-DOS, whereas real-time OS is Windows CE, QNX, VxWorks, micro C / OS2. So we'll see what is a real-time purpose operating system, because all medium and large scale embedded systems they use this operating system. So the kernel has a real-time kernel. In complement to the conventional OS kernel, real-time kernel is highly specialized. It contains only the minimal set of services. Okay, it contains only the minimal set of services required for running the user applications. So these kernel services are run in order to assign the user with some hardware resources. So here we, instead of doing all the services, only some minimum set of services are required for running the user applications. The basic functions of a real-time kernel are task or process management, task or process scheduling, task or process synchronization, error exception handling, memory management, time management, and interrupt handling. So these are the services provided by that. First one is real-time kernel task or process management. So whenever this real-time kernel sees there are multiple tasks, it allocates memory space for the task, loads all the tasks into the memory space, allocate the system resources as per the requirement of each task, then set up a task control block. So once the tasks are assigned some memory and they are allocated memory space and they are allocated system resources, it sets up a task control block for each task. See, all the tasks will be saved in the memory space, and we are going to allocate resources for them. Then in such a case, you have to create a TSB. This TSB is unique for each task, and it just see, whenever there is a task is completed, you have to delete it. Whenever there is a task to be initiated, you have to uh, uh, create a TSB for it. What is the purpose of TSB? Is it is holding the information corresponding to a task. It contains the following set of informations. A TSB usually contains the following set of informations. Each task will have a TSB. TSB will tell what are the resources it is having, what is the task ID. Task ID means each task is identified by a task ID called a task identification ID. Task state, that tells about the current state of the task. Task type, it indicates which type of task, whether it is a hard real time or soft real time or a background task. So it should identify among the tasks which is priority, which is must be completed fast, and which is linked to other tasks. In such a way, you have to decide which task must be done first. So for which we are doing is we are seeing whether this is a hard real time. Hard real time means you have to see that the result is deterministic, or soft real time or background task. And there is a one more information related to TSB, like task priority. If any task is means there is a information block called task priority, where if one is kept, it seems that corresponding task is given first priority. Task context pointer pointing for context saving. Task memory pointer pointing to the code memory, data memory, and stack memory. Task system resources pointer pointing to the system resources, semaphores, mutex, etc. used by the task. Task pointer pointers to the other TSPs, other parameters and relevant. So, as here we can understand real-time OS is going to see all the tasks, and it is going to allocate all the memory spaces required for task, allocate system resources. Then it has to do task scheduling and prioritize the tasks by creating TSB for each task, and the TSB contains of some information like task ID. Each task is identified by its task ID, then its state, its type, its priority, its memory requirement, and pointer, all are linked to each TSB. The parameters and implementation of TSB are kernel dependent, and the TSB parameters vary across different kernels based on the task management implementation. So first one is task or process management. The kernel services is task or process management. The next service of your kernel is task or process scheduling. What is scheduling? Once you allocate memory to all the tasks, you have to deal with sharing the CPU time with tasks, for which a scheduler, a small program or algorithm which performs scheduling of the task to provide a deterministic behavior. And the next kernel service is called a task or process synchronization. It must deal with the synchronizing the concurrency of resources while it is sharing among multiple tasks, and communication must be considered between communication must take place between various tasks. And another task kernel service is error or exception handling. What is this error or exception handling? It is dealing with registering and handling the errors. Deals with register means it has to identify the errors and exception errors, and it has to handle the errors occurred, or it has to exempt them, which are exempt them which are raised during the execution of the tasks. Next, insufficient memory, timeouts, deadlocks, deadline missing, bus error, divide by zero, unknown instruction execution. These all are the examples of errors or exceptions. So whenever you occur insufficient memory, you have insufficient memory, timeout, unknown instruction execution, this error or exception handling takes place, and this is identified by your kernel service. Another kernel service is error or exception can happen at the kernel service or at the task level. Deadlock is an example of a kernel level exemption, whereas timeout is an example of, see, each task it is executing, and each task is provided with some time. So if your CPU is allocated some time for a task, and if task is not unable to be done by the processor due to hardware failure and anything, so that is called a timeout. Timeout is an example for task level exemption. Deadlock is an example for kernel level exemption. The operating system kernel gives the information about the error in the form of a system called API. So your operating system kernel gives the information about the error in the form of a system call. So you are saying that this RTOS is doing various services such as task process management, task scheduling, error exception handling, deadlock. The memory management is slightly different here compared to your general purpose OS. Here, as the number of tasks increases, the memory size increases. The time allocated will also increase depending on the size of the memory needed to be allocated. So if you allocate more space for one task, so corresponding time utilized for executing the task will also be more, and initialized memory block consumes more allocation time compared to uninitialized memory block. So if you initialize the memory block, it consumes more allocation time. Next, since predictable timing and deterministic behavior are the primary focus of an RTOS, RTOS achieves this by compromising the effectiveness of memory allocation. So here, your embedded system results must come as early as possible. So predictable timing, it must give the results, and they must be correct. Means they must be deterministic. In such a case, the primary focus of RTOS must be effective utilization of the memory allocation. So RTOS generally uses block-based memory allocation technique instead of a actual dynamic memory allocation used by the general purpose. So in general purpose OS, there is a dynamic memory allocation, but whereas in RTOS, we are seeing that it is a block-based memory allocation. So RTOS kernel uses blocks of fixed size of dynamic memory. RTOS kernel uses blocks of fixed size of dynamic memory, and the block is allocated for a task on a need basis. So we are seeing that your RTOS kernel uses blocks of fixed size of memory for its tasks, and once a task is allocated, uh, once the task is allocated on a need basis, the blocks are stored in a free buffer. So the memory is divided into blocks of free size, where your RTOS kernel requires memory allocation and on a need basis, and the blocks are stored in a free buffer queue. So most of the RTOS kernels allow task to access any of the memory blocks without any memory protection to achieve predictable timing and avoiding the timing overheads. And the RTOS kernels assume whole design is proven correct and any protection is unnecessary. The memory management of RTOS is slightly different. A few RTOS kernel implement virtual memory concept for memory allocation. So in some few RTOS kernels implement virtual memory concept for memory allocation if your system supports secondary memory. In the block-based memory allocation, a block of free memory is always allocated for tasks on a need basis. In the block-based memory allocation, see, there are two methods of memory allocation: block-based, okay, and dynamic memory. Here, block-based memory allocation, a block of fixed memory is allocated for all the tasks, uh, and that is on a need basis, and it is taken as a unit. Hence, there will be no memory fragmentation issues. The memory allocation can be implemented as constant functions, and thereby it consumes fixed amount of time, and this leaves the deterministic behavior of RTOS kernel untouched. See here in this point, we are saying that the memory allocation can be implemented as a constant function, and thereby it consumes fixed amount of time for memory allocation. So till then, the deterministic behavior of RTOS kernel is unlocked, untouched. Interrupt handling is another kernel service where whenever there is an interrupt is occurring, the task, an associated task requires immediate attention. So it can be synchronous or asynchronous. So interrupts which occur in synchronous with current executing task is known as synchronous events. Usually the software interrupts fall under the synchronous events. Examples: interrupt divide by zero, memory segmentation error are examples of synchronous interrupts. So interrupts which occur in synchronous with the usually the software interrupts fall under the synchronous interrupt category. Divide by zero, memory segmentation error are examples of synchronous interrupts. For synchronous interrupts, the interrupt handler runs in the same context of interrupting task. Asynchronous interrupts are interrupts which occur at any point of execution of any task and are not in synchronous with the current executing tasks. So these interrupts are generated by external devices connected to the processor, timer, or overall interrupts, serial data reception, transmission interrupts are examples of asynchronous interrupts. The interrupt handler is usually written as a separate task and it runs in a different context for a asynchronous interrupt. Priority levels can be assigned to the interrupts and each interrupt can be enabled or disabled individually. So as we're telling, there are interrupts occurring, we can assign priority level to the interrupts and each interrupt can be enabled or disabled. Most of the RTOS kernel implements nested interrupts architecture. What is this nested interrupts is? Interrupt nesting allows the preemption of an interrupt service routine, servicing an interrupt by a high priority interrupt. Interrupts inform the processor that an external device or an associated task requires immediate attention of the CPU. Accurate time management is essential for providing precise timing reference. The time reference to the kernel is provided by RTC, real-time clock hardware chip. This RTC will hold the information about the events occurring at what time, how much memory is allocated. The hardware timer is programmed to interrupt the processor at a fixed rate. The timer interrupt is referred as timer back tick. The hardware timer is programmed to interrupt. The hardware timer is programmed to interrupt. The hardware timer is programmed to interrupt the processor at a fixed rate. The hardware timer is programmed to interrupt the processor at a fixed rate. The timer interrupt is referred as timer tick. So what is a timer tick? A timer tick is taken as a timing reference by the kernel. So it may vary depending on the hardware timer. Usually timer tick is varying in microseconds. The time parameters for the tasks are expressed as multiples of timer tick. So different tasks will be executed with different times. So they will be allocated certain time in reference to your time ticks. The system time is updated based on the time tick. If the system time register is 32 bits wide, time tick interval is microseconds, then the system register will be reset in how much time is indicated as time management. 232 into 10 power of minus 6 by 24 into 60 into 60, which comes 49,700 days, which is nothing but 1.19 hours. And this timer tick interval, if it is 1 milliseconds, the system time register will be reset in if it is 1 milliseconds, it will be reset in 50 days. The timer tick interrupt is handled by the timer interrupt handler of the kernel. So this timer tick interrupt is handled by the timer interrupt handle of the kernel. The timer tick interrupt can be utilized for implementing following factors: save the current context. update the timers in a kernel, increment the registers with count, activate the periodic tasks which are in idle state, delete all the terminal tasks and associated data, load the context for the first task. A real-time operating system will strictly adhere to the timing reference. A hardware real-time must be under meeting the deadlines of a task without any slippage. Missing any deadline may produce catastrophic results for finding real system permanent data loss irrecovery. So there is something called real-time operating systems, hard real-time and software real-time systems. And ATM is a typical example of software real-time systems, and hardware real-time systems is visual critical systems. Um, so the presence of human in the loop for task introduces unexpected delays in the task's execution. Most of the hard real-time systems are automatic and does not contain a human in the loop. So with this, we'll stop our video. We'll cover our next topic, tasks, process threads in our next video.